Hey guys, all right, we're going to get to the main part of week one. Most of the information that is new, as well as extensive, if you want to say, it will be coming from the second part, which is looking at rational functions with the vertical asymptotes, horizontal and removable discontinuities. Okay, so this number two notes handout. That's really the main part of week one that will be definitely new than what you've seen before. Okay, so let's go ahead and begin. So we have zeros. So zeros are otherwise called x-intercepts. Okay, and this is where the graph is going to cross the x-axis. So it says the zeros of a rational function are where the y value of the graph is equal to 0, okay? And those are x-intercepts because whatever those x values are, we know that their y value is, in fact, equal to 0. Since the function has a numerator and a denominator, which part do you really see to set equal to 0 to solve for the x-intercepts? Okay, so a couple things that I want to talk to you about right off the bat is we know that any number, we're going to use this pound sign, otherwise this hashtag symbol, to represent any number. So a number. Okay, and we're going to say a number that is not equal to 0. So any number, it could be negative 10, it could be 20, it could be a million, as long as it's not 0. Okay, so when we take 0 times any number that's not 0, we're going to get 0. But with this rational functions unit, something that we have to think about is what does a number, again, that's not 0, divide by 0 give us? Or flip-flop, what is 0 divided by a number, again, where this number is not equal to 0? Okay, so let me highlight it real quick in blue. This number not equal to 0, that means that this cannot be 0, this cannot be 0, and this, or not necessarily cannot, but is not 0. Okay, so three truths. Anything times 0 is going to equal 0. And any number divided by 0 will be undefined. And 0 divided by any number, again, that's not equal to 0, will equal 0. So if I said like 0 divided by 3, that's 0. 0 divided by negative 3, this is 0. But if I said, what is 3 divided by 0? Well, this will be undefined. And what would negative 3 divided by 0 be? That too will be undefined. So from this, we're learning that we cannot divide by 0 because we will get undefined. Okay? But we can take a 0 and divide it by something other than the number 0, and it will in fact give us the answer of 0. Now, what does that all mean? Okay, so let's look at these first three rules. It says, if f of x is equal to the numerator with x divided by the denominator with x and are factored, okay, so this is huge. We're going to do a lot of factoring. So when we were looking at quadratic formulas with like x squareds, and we'd break them up into two separate binomials that were multiplied, right there, we're going to do a lot of that in this unit again. So we're going to bring that factoring unit back for sure. Okay, it says the values of x that make the numerator, okay, equal to 0 are the zeros of the function. These are the x-intercepts. Now, there is a caveat to that, and we'll talk about that here in just a bit. So when the numerator is equal to 0, that's when we're looking at the x-intercepts, okay? But when the denominator is equal to 0, let me highlight that. When the denominator is equal to 0, then those are the vertical asymptotes, or something that you will see later of could be possible removable discontinuities. So that's a new thing that we're going to learn, okay? So this is the instance, and this is the instance that will give you the x-intercepts and the vertical asymptotes, but this is after you have accounted for removable discontinuities. And we'll talk about what those mean here in just a bit. So RD, removable discontinuities. Okay? So the existence and location of a horizontal asymptote. So the horizontal asymptote, remember the horizontal line that the graph will approach, talking about in behaviors, on the degrees of the polynomials that make up the rational function. Okay, so this next part is going to strictly talk about the horizontal asymptotes, and I'm going to talk about these next three rules. So when I want to find the horizontal asymptotes, it has to be, it says let f of x equal the numerator with x over the denominator with x. They're both going to be shown in some kind of standard form. And the standard form for a quadratic, we know, is y is equal to ax squared plus bx plus c. We know that from units past. Now, if I want to look at this and I actually want to see where is the horizontal asymptote going to happen, I need to look at an acronym. Okay, it's going to be BO2, then it's going to be BOBO, and this last one's going to be Betsy, if you will. So we're going to say BE. These are acronyms for what you'll see they represent here in just a bit. So BO2, BOTU, is going to stand for bigger on top, then it's going to be undefined. Okay, so bigger on top, undefined. And we get those from BOTU is bigger on top, undefined. And this is talking about specifically the horizontal asymptotes. All of these three are going to represent the horizontal asymptote of the function. Okay. However, if the degree of the numerator is less than, so up here it was when it was greater than, if the degree of the numerator is less than the degree of the denominator, then we're going to use BOBO. And BOBO means bigger on bottom, then it's 0. So y is equal to 0. Okay, so again, bigger on bottom, y equals 0. Bigger on bottom, y is equal to 0. And on a graph, that looks like this right here. Y equals 0 would be at the x-axis. That would be the horizontal asymptote. Okay, and then this last bit is going to say Betsy, and that stands for, let me go ahead and write that right below. We're going to put, bottom equals the top, then it's the coefficients. Okay, so it's the coefficient that you'll see. So when the leading coefficient of the top, you're going to take it and divide it by the leading coefficient of the bottom. So the leading coefficient, and the leading coefficient, just a reminder, is the number that's in front of the biggest power of x. So the leading coefficient of top is going to divide by the leading coefficient of the bottom. So coefficient of the bottom. You're going to see all that here in action here in just a bit, okay? But nonetheless, this is after the removable discontinuities have been accounted for, okay? So let's go ahead and move forward and look at some examples. First of all, identify the zeros and asymptotes, okay? So the zeros of the function, I'm talking about when does it cross the x-axis, the x-intercepts, if you will. And the asymptotes are going to be the vertical asymptote and the horizontal asymptote. Okay, so we know that these rational functions, they have a vertical asymptote of some kind, which is default the y-axis. Okay, and then they also have a horizontal asymptote that's default as the x-axis. Okay, what we're trying to do is we're trying to identify it from this given equation here. And this is how we do it. This is a pure rational expression. Okay, it is a function because it's f of x. So we're going to call this a pure rational. And the first step to solving all these pieces is to factor. Factor, okay? So if I factored the top, it would give me x minus 3, and it would give me, x minus 4 actually, and it would be x plus 1. Quick reminder, these two will multiply to get this term. These last two will multiply to get the last term. And then this negative 4x And then this one here, as far as a positive x, will result in a negative 3x, which, of course, is my b term that you see here. Okay, so this is definitely if you need to go back to previous units to review, we definitely encourage that to make sure that your factoring is on point. Okay, and this is all going to be over x. And now this is f of x. So all I did to get from here to here is I factored the top and the bottom. Now, from here, there's nothing that looks the same. There's not a factor that's the same on the top and the bottom that we could cancel to a form of 1. And you're going to see here in just a bit, that's accounting for removable discontinuities. We don't have those right now. So we can go straight to what we were saying over here on this previous slide of the numerator is going to give me, so let me highlight that right here. The numerator is going to give me the x-intercepts. And then the denominator is going to give me the vertical asymptotes. And then we'll do these rules here to see what are the horizontal asymptotes. Okay, those rules right there that you saw with Botu, Bobo, Betsy. Okay, so let's go ahead and look at these pieces. So if my x-intercepts come from my numerator, let me go ahead and make a x-intercepts kind of column. That means I have one that is x minus 4 and one that is x plus 1. Okay, and what I'm going to do is I'm going to set them equal to 0. That was the rule that we saw back here. We're going to set them equal to 0. Okay, so if I solve for x, I have x minus 4 is equal to 0. Move everything over so that x is alone. And the same thing here, so that you would get x is negative 1 and 4. Or negative 1, 0 as a point, and 4, 0 as a point. These are the two x-intercepts, here and here, and you could list them out like that. Either notation is correct. Okay, so the zeros of my function, that's what I was looking for up here. I'm going to list the zeros are at x is equal to negative 1 and 4, or if you wanted to list them as points, we could say negative 1, 0 and 4, 0. Our preference is that you make sure that you understand that they're the x values, so we'd prefer you to write it like that, showing the actual x-intercepts. Okay, now let's look at the asymptotes. So these asymptotes right here, we're going to look at the vertical, just the vertical asymptote first. So let's look at the vertical asymptote. Okay, so the vertical asymptote from this last slide was whenever I would set the denominator equal to 0. Okay, so this denominator is equal to 0 right here will give me the vertical asymptotes. So let me go ahead and highlight that actually with blue. Okay, so this is our VA. So if I look at my denominator, all I have is x. So when I set it equal to 0, there's nothing really to get by itself. There's nothing to solve. So that already is my vertical asymptote. Okay, so now I have my zeros of the function. I have my vertical asymptotes. This came from the numerator, set equal to 0. This came from the denominator, set equal to 0. And now I want to look at this acronym down here of Botu, Bobo, Betsy to see where is my horizontal asymptote going to exist. So the horizontal asymptote, here we go. So I'm going to look first at my original standard form, not the factored form. Okay, so this right here is the factored form, and that gave us these two pieces. But then I'm going to go back to my original standard form in order to get, let me highlight that in green, in order to get the horizontal asymptote. Notice the two different forms that you're going to use to get the different pieces of these attributes of rational functions. So if I looked at the biggest degree of the numerator, I see that it's 2, because that's x to the 1, x to the 0, because nothing is there as far as x. Okay, so the biggest degree of x is x squared. The biggest degree on the bottom is x to the first. So right now, this is bigger on top. And we know from back here that bigger on top is going to be undefined. Okay, so this one will actually not have a horizontal asymptote. Okay, there's going to be more to it, but for now, we're just going to say that there's not a horizontal asymptote. So we'll just say none. Okay, so if I were to go to Desmos and put this right here, this equation. Let's verify these pieces just to make sure that they, in fact, are accurate. Okay, so let's take off our standard default, and we're going to put something that looks like this. So we're going to say x squared minus 3x minus 4 is all divided by x. Now we don't need these parentheses. And there's our equation. And you notice, if I zoom out, we don't see a horizontal line that the graph approaches. It actually looks like there's a slanted line that it approaches as you go to the right and as you go to the left. But nonetheless, let's verify the pieces that we were looking for. We were looking for, are there x-intercepts at -1 and 4? And sure enough, if I zoom in, you see at -1 and 4, those are the x-intercepts. I also look back and there's a vertical asymptote at x is equal to 0. X is equal to 0 is the y-axis, this vertical line at x equals 0. And sure enough, that does hold true, and it shows that this vertical asymptote does exist. But there's none for the actual horizontal asymptote. Okay, so that's what we have for that first one as of right now. Okay, so now let's go ahead and move on to this next example and see the pieces. I'm going to start picking up the pace to make this video not as long, but then I will still mention what we're doing as we go through piece by piece. Okay, first step. This is in pure rational form. Because it's in pure rational form, I'm going to factor. So x minus 2, and then difference of squares, x plus 1, x minus 1. This is my factored form. Now, to identify the zeros, I will set the top equal to 0 and solve for x, which happens at 2. So my x-intercept becomes, and you could say x-intercepts, or you could say zeros. So let's just say 0 since that's what it was saying. The zeros of the function, aka the x-intercepts, will occur at x is equal to 2, or 2, 0 as a point. Okay, that's the first part. The asymptotes. Okay, so now we're going to look at the asymptotes, and let's start with the vertical asymptote. The vertical asymptote is when the bottom is set equal to 0. Okay, so I have two pieces. I have x plus 1, and I have x minus 1. So if I get x by itself, there's one of them. And if I add this to the other side, I'm going to get a positive 1. There's the other. So I have a -1 and a positive 1, so I have 2. I'm going to put x equals -1, and x is equal to 1. Two vertical lines. Okay, so now let's look at the last piece, the horizontal asymptote. Now remember, the horizontal asymptote is not going to be from this pure rational factored out form. The horizontal will go back to the original one, and it's going to focus on what's the biggest power of x in the numerator and the biggest power of x in the denominator. Okay, and we see the denominator is bigger. So when we come back here, we see Bobo. Bigger on bottom, it's going to be y is equal to 0. So over here, because it's bigger on bottom, we're going to put y is equal to 0 is our horizontal asymptote. Okay, so let's verify this just real quick with Desmos. So up here, we're going to put our original. We're going to put, we're going to put x minus 2. And down here, we're going to put x squared minus 1. And sure enough, let's zoom in, and you will see exactly the pieces that we verified. We have an x-intercept at 1 and -1, or sorry, a vertical asymptote, that is. Vertical asymptote, a line right here at 1, and a line right here at -1. And it's as the graph is approaching, but will never hit. Think of those vertical lines. We also see that at x is equal to, the x-axis at y is equal to 0, right here, is showing a horizontal asymptote. Now, careful, because the horizontal asymptote, we said before, was where the graph would approach but never hit. Now, what it really means is as you go to infinity, way over here, it will approach it and never hit. But in between, can it actually go through? The answer is yes, it can go through, but in behavior, is talking about at the ends. At the very, very far right, it will approach 0. And at the very, very far left, it will approach 0. That's what horizontal asymptote means. Okay. But yes, it can cross intermittently in between. Okay. And then our last part is, what was the x-intercept that we found? We only found one of them at 2, 0. And sure enough, at 2, 0 is where it crossed the x-axis. Okay.